The second part of 10.2 has us using the combination function on our calculator to help recognize patterns in expanding binomials. I know, that sounds like a lot. Today's not really a probability or just a plain combination type day. We're going to start off just by recognizing some patterns in expanding the binomial x plus y. If we raise anything to the 0 power, it's just 1. We know that rule from chapter 5. If we raise this, if we expand this binomial just to the first power, that's x plus y. But I'm going to write specifically 1x plus 1y. If we were to FOIL x plus y squared, we would get 1x squared plus 2xy, we'd have like terms in the middle, plus 1y squared. If we kept going and we FOILed that again for x plus y to the third power, we would get 1x cubed plus 3x squared y plus another 3, but xy squared this time, plus 1y cubed. I'm saving us a little bit of time by showing the FOIL, but that is the answer you'd get. If we take x plus y to the fourth power, the focus here is to look at the numbers that we're generating as well as the exponents. If we multiplied x plus y by itself 4 times, here's what we would get. We would get 1x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the fourth. All right, there's one more round. If we multiplied x plus y 5 times, here's what we would have. Multiplying that parenthesis out 5 different times, we would end up with 1x to the fifth plus 5x to the fourth y plus 10x to the third y squared plus another 10x squared y to the third plus 5x times y to the fourth, and we'd end with 1y to the fifth. And that's the expansion. Let's take a look at all of these solutions. What do you notice? Take a look at the coefficients, the x's and the y's. There are some patterns here. Our goal is to be able to figure out what these patterns are and to see how this fits in to chapter 10. Some things that I see when I look at this, I notice that every answer starts with a 1, and every answer has a coefficient that ends with a 1. Notice the x's start with the big exponent and kind of make their way smaller until there's none at all, but the y values start with a small exponent until they reach the biggest one. And there are some patterns within the numbers. I have a 1, and then I have 2 1s, and then I have 1 2 1 in between, 1 3 3 1 for my coefficients. In the next row, 1 4 6 4 1, so there's kind of a pattern there, and then 1 5 10 10 5 1. These numbers don't just happen magically. There's an actual reason that's related to combinations. Pascal's triangle is defined as a triangular pattern of the rows of NCR, using your combination function on your calculator. Now, the smallest value that we can work with is 0. We start then with the 0 row, and that means you have 0 to pick from and you're not picking any of them, which I know sounds kind of strange, but that's what starts us off as x plus y to the 0 power, and that's where we got that 1. Now, in the first row, n equals 1, but we know we can either choose 0 or 1 as an R option. So 1C0 on your calculator and 1C1 are both 1 on that right-hand side. This over here on the right-hand side is the actual Pascal's triangle, but the NCR rule in the middle is simply how to calculate it. Notice in that second row there are 3 terms. So they start with an n value of 2, and then we use an r value of 0, 1, or 2. Now, if you type them all into your calculator, you would get 2C0 is 1, 2C1 is 2, and then 2C2 equals 1. And this pattern continues. So again, let's try to look at what we recognize. What do you notice and what do you wonder about this triangle? Some things, again, that I see, take a look at those patterns. Now, the triangular component is kind of cool. If we look at how these numbers relate to each other, notice each row starts and ends with a 1. But in between, if I go from row 1 to row 2, I can add these 2 numbers up above to get that number right below, right in between them. If I drop down to the next row, I can add the 1 and the 2 to get a 3, and I can add the 2 and the 1, and I also get a 3. And that pattern will continue. In the next row, 1 and 3 give me 4, 3 and 3 would give you 6, and 3 and 1 would bring you back to 4. And that will continue on for as many rows as you want to generate in this triangle. In row 5, I have the 2 numbers up above to get that second term, 4 plus 6 to get the third one, 6 plus 4, and then 4 plus 1 again. So notice row 5 has 6 terms because we start with 0 and we go all the way up to an R value of 5. All right, pause the video and see if you can generate the numbers in row 6. Go ahead and plug them in over here on that right-hand side. When you think you have them all, press play and we'll see how you did. There are 2 ways you could have gone about this. If you follow that triangular pattern, we start and end with 1. To get the next term, I'm just going to add the 2 right above it. 1 plus 5 is 6. To get the next term, 5 plus 10 is 15, and so on. In row 6, there are 7 terms, and the pattern is 1, 6, 15, 20, 15, 6, 1. We could have also used combinations. We could have started with n equals 6 and r equals 0. So that would be 6c0, 6c1, 6c2, and so on. Plugging those values into our calculator would generate the exact same row. All right, looking back at the big picture again. Specific terms in a given row. How do you determine the third term in the 5th row? If I look at the 5th row, count over 1, 2, 3, that's the answer you would have, 5C2. So the 5th row matches here, but if I want the third term, notice my R value is 1 less. So let's see if we can apply that. Oopsie, and I can't even spell. Let me try to get 1 less in there, and then we'll move on to the next example. There we go. R is 1 less. If we were going to move on to a row further down in Pascal's triangle, how could we determine the 8th term in the 11th row? So the 8th term in the 11th row. This means n is 11, but the 8th term we would do 8 minus 1. We would do 1 less. So R would be 8 minus 1. To get the coefficient for the term in the 8th term in the 11th row, we would do 11C7. I'm going to go ahead and plug that in, 11C7. That means in the 11th row, if you had all those terms multiplied, the coefficient out in front would be 330. That would be the coefficient. How about the 4th term in the 7th row? So 4th term, 7th row. That means n equals 7. And if we want the 4th term, R is 1 less than that. 4 minus 1, which is 3. We would do 7C3, and that would give you the coefficient in front of that 4th term, and that would be 35. So how does this relate to us in Algebra 2? Flip it over to the next page, and I'll show you. Binomial expansion using combinations to help us expand binomials. This is just a way to recognize patterns and help us determine an answer without having to FOIL a whole bunch of smaller parentheses. For example, multiply x plus 2 to the 4th power. Now that we have a 2 instead of a y, we'd have to write this out 4 times and try to FOIL it all together. Therefore, instead of supersize FOILing this whole thing and trying to combine like terms, let's take a look at how that Pascal's triangle would be helpful for us. Notice the exponent that we want to expand is 4. So that means we're in row 4 of Pascal's triangle, meaning we'd have 5 terms. So each of those terms would have a coefficient using NCR. N equals 4. So we're going to have this little chart here that I've created for us. We've got the NCR. We've got our first part of the parenthesis, which is x, and then the second part of the parenthesis, which is 2. So the parentheses are really useful in this step. We want to be careful using these parentheses. All right, so here's how it works. We know what our n value is. It's 4. So in our first term, just like Pascal's triangle, we actually start with 1 less for our r, which is 0. In the second term, 1. In the third term, 2, and so on. You'll know you're done with Pascal's triangle when the n and the r value are a match. So that's all you do in that first column. The x's are next, and if you notice in the way we expanded at the very beginning of the lesson, we start off with the same exponent as the original parenthesis. We're going to get x to the 4th power. And then that decreases until it goes to 0. x2, x1, and then x to the 0 power. The 2 does the reverse. The 2 is that last part of the parenthesis. It's going to start with 0 and then work its way up. And you'll know you're done with that 2 when it matches the same exponent as the original problem. What we do now is just focus on multiplying each part together in the rows. So now we go kind of to the row version of this and we multiply everything together. For example, 4c0 times x to the 4th times 2 to the 0. 4c0 on Pascal's triangle is 1, x to the 4th is x to the 4th, and 2 to the 0 is also 1. If we multiply those all together, our final answer is 1x to the 4th. And then you do the second row, same thing. 4c1, you can either plug it into your calculator or use Pascal's triangle, is 4, x to the 3rd power, and now this time 2 to the 1st power is 2. And if we multiply these together, we get 8 x to the cube, or x to the 3rd power. And you continue that pattern. 4c2 is 6 times x squared. 2 squared is 4. 6 times 4 would be 24. Continuing on. 4c3 would go back to 4. X to the 1st power is x. 2 to the 3rd power, be careful here, is 8. 4 times 8 is 32. And last but not least, 4c4, that last value in any row of Pascal's triangle is a 1, just like the first value. X to the 0 is also 1, and 2 to the 4th power is 16. 1 times 16 stays 16. Notice we have 5 terms here, and these, well, I don't know what's happening, hang on. These 5 terms, I don't even know what that just did, would give us our final answer. So the expanded form for x plus 2 to the 4th power is x to the 4th plus 8x to the 3rd plus 24x squared plus 32x plus 16. That takes the place of having to supersize FOIL 4 times and trying to combine like terms to get this same result. And I think we'll stop there. We'll work on the rest of the problems in class.